Okay, so we are going to start our session today for the thesis defense. Mateo Coles is going to present his work for the master degree, and I think that you have around 25 minutes at the maximum. So please go ahead.
Okay. Thank you, Rosa, for the introduction. So let me introduce my master thesis, which is titled as Neural Networks in Deep Quantum Classical Architectures. The work is divided as follows. First, I will give you an introduction about reservoir computing and quantum reservoir computing, to then present our model that we have established, which is an hybrid model. And after that, we will show the result and give some conclusions about our model. So, as we know, artificial intelligence has acquired a relevant importance in the recent days, and it's a broad field. And within it, we have machine learning that allows computers to learn from data. And the subset of machine learning are neural networks, where deep architectures with many hidden layers can struggle in training due to the propagation algorithm that can fail. So a lightweight solution to this problem is provided by reservoir computing. In reservoir computing, internal connections are fixed and initialization and remain unchanged. And this was first proposed with these two proposals of the Echo State network and liquid state machine. And the structure is the following. First, we have an input sequence, which is inserted to a substrate. And the states of this substrate are updated according to the previous input values. Then this degrees of freedom of the substrates works as computational nodes to output to map the output time series by simply linear regression. The advantages of these kind of architectures is its training simplicity, because only is required training in this output layer with linear regression, and also it's multitasking and sequential trainings, since we only have to change the weights of the output layer to change the task, and also the versatility of physical systems. We are not restricted to use neural network kind of architectures. We can use any physical system, but it must satisfy three properties that are the echo state property, which is independence of initial conditions, the fading memory, that is for getting far past inputs, and the separability of different inputs, time series. So the versatility allows us to introduce a new framework, which is quantum reservoir computing, which is this first proposal, and uses a quantum system as a reservoir. However, it can be also generalized to quantum inputs and quantum tasks, as reviewed in this paper. So why is so interesting quantum reservoir computing? The main motivations are the exponential degrees of freedom that we can access because of the Hilbert space. For instance, a reservoir of L qubits, the degrees of freedom expanded to 4 to the L minus 1. Also, it's feasible implementation in noisy intermediate scale quantum devices, and its name suggests, also quantum reservoir computing is ideal to process quantum data time series. So the output map in the output layer, now the computational nodes are the observables that we measure in our quantum system. And as you can see, these expected values are linear functionals of the state. So the problem that we want to face is that quantum reservoir computing cannot reconstruct nonlinear functionals of the input state. For instance, the purity of the system cannot be achieved by quantum reservoir computing. So there are previous research about that, but in different contexts, for instance, in static stacks, in the context of quantum state learning machines, and also an hybrid setup proposed using a quantum optical platform. With our work, it's based on this kind of setup, and we propose a hybrid setup composed by quantum reservoir computing and classical reservoir computing, which is represented by an echo state network. And we try to take advantage of the processing of quantum series in our quantum part, and as well as the information spread across the degrees of freedom to compensate the short memory that our system will present, and also our system cannot perform nonlinear tasks. On the other hand, the echo state network will present a long memory and is strong processing nonlinear tasks. The problem is that it needs tomography of the quantum input, needs the classical values of the schematic that we inject, and as we will see, requires all the quantum information, not only this part of the information can work. So this hybrid architecture will enable to tasks that neither component could achieve on its own. So now that I've set the motivation, let's present the hybrid setup. But this is just to have an idea, but because now we focus on each component on itself. First, let's focus on this part, that is the input injection, the quantum supercomputing. So we inject this input state from 1 and 10 step scale via a completely positive trace preserving map. This input injection is done by the erasure information from qubit 1 and injecting the U1. And then in the step 2, we perform unit, we let the system evolve unitarily according to the Hamiltonian dynamics for a time interval delta t. Then the measurements and the observables are used as computational terms. So these Hamiltonian dynamics are established by this Hamiltonian, where we have a reservoir of L qubits all connected with transverse field and local disorder. The coupling values are local disorder are uniformly generated within this interval. And depending on the value of H and the disorder strength, we can find different dynamical phase transitions that are given by this metric that depends on the energy level statistics. So here we can identify two main regions represented by these follows. The orange region, which is the non-ergodic region, and represents an absence of transport and quantum information.
Maybe at the beginning it was working and then something happened. Si quieres usar el demás.
Ah, está. No. Ah, vale.
Sí.
¿Sí?
Vale.
Okay, vale. So we have our dynamical phase transition heat map, and we can identify the orange region, which is the non-ergodic. This is represented by an absence of transport. As you can see here, each time that we inject an input, the information remains localized, and the other qubits reservoir remains unresponsive. Whereas in the ergodic region, there is an splitting of initial local quantum information. And as you can see here, once the input is injected, evolves unitarily, thermalizing, and the other qubits represent correlated dynamics. We will not show here the optimizing plots, but we have seen that the ergodic region yields to better results, and we consider this point for quantum reservoir computing. Going to the classical part, we consider an echo-state network, which is a recurrent neural network with random connections in the substrate. And the state of the echo-state network updates with this nonlinear map. So that depends on the previous state and the input at that step. Sorry. The nonlinear function that we consider is this logistic function, the internal connections are randomly generalized, and the hyperparameters, the feedback and input gain, are optimized before everything. So here we optimize this parameter for linear and nonlinear tasks, and these green areas represent the optimal values of GNL. So now we have set the we have explained which are the components of our hybrid setup. So now it's important to clarify how this hybrid setup works. Its training is represented in a two-step process. First, in the quantum, when the input is injected in the quantum reservoir computing, this preprocessing layer, which is the output layer of the quantum reservoir computing, is trained to reproduce the state memory task, which means that it's trained to reproduce each block vector component of the input at a delay tau QRC. This delay will be referred as preprocessing delay. And once this preprocessing layer is fixed, we send these predicted delayed outputs as inputs to the echo-state network. So the idea is, with a quantum input, this preprocessing step sends an estimation of the input with classical values to the echo-state network. And then when we use these inputs to the echo-state network, the output layer of the echo-state network is trained to achieve different tasks that we can consider, such as the purity or von Neumann entropy, that are nonlinear, but also can perform linear tasks, such as the same as before, that is the state memory task. This is important to recall that this value, that is the preprocessing delay, supports the echo-state network by retaining some memory in the quantum reservoir computing. But we will see that sometimes it's not helpful to distribute this delay. We can set this distribution as 0. So if we set this preprocessing delay as 0, it's important to recall that it's not equivalent to the full echo state network, because even with this situation, we are performing measurements at delta t, and this task is achieved at the present state. So before delving into the results of our hybrid setup, we want to see if our preprocessing layer can reconstruct the state from a restricted set of measurements. To see this, we set the quantitative computing task of the preprocessing layer that we mentioned before. And we want to see if we consider alpha axis observables along this set of observables along one axis, we can get information of all the directions of the input state without the necessity of measuring in non-commutable directions. So to see this, we use the capacity of asymmetric, that is just the square of the Pearson correlation coefficient, namely that at 1 is perfect value, at 0 is cannot be performed the task. And we consider here measuring only Z observables. We can see how we can only get information of the Z projection of the input, whereas with X and Y, we can see how we have information of the Z and an additional direction. But the memory is not, memory fails abruptly at tau 1, so this system has no memory. So now that we have seen how the preprocessing layer works, we want to see how this is affected in the hybrid final performance. So to achieve this, we compare the quantum reservoir computing standalone, the standalone echo state network, and the hybrid setup to see the performance of the architecture that we propose. The components that have quantum part consider the set of observables that we mentioned before, and the classical echo state network, when we restrict to only alpha measurements, will be this alpha projection of the input. And so from now on, we consider the normalized mean squared error as metric, so the closer to 0, the better. To see this, we perform a simple nonlinear task, which is the purity memory task, that is recalling the purity at delay tau. And we do for different kind of set of observables. We can see that represented by this red line, the quantum reservoir computing, as expected, fails in all situations. And in the standard echo state network, only performs correctly if all the tomography is injected to the classical network directly. But for the hybrid part, we have a more complex behavior. For instance, in the Z, which is considering only the Z observables, we don't have any improvement as expected because it doesn't give any additional information. But with X and Y, there is a small improvement, but not significantly. But if we join the measurements of X and Y, so we're measuring in two directions, this information complements and we can get a performance which is equivalent to the case if we have all the information. So as a takeaway message, we see that we can extract nonlinear features from limited measurements, unlike its components alone. And these trends hold similar for across the different tasks. But as we have seen, the hybrid performance can be constrained by the short memory of the quantum preprocessing layer. So we ask if we can artificially extend this memory. So the answer lies in time multiplexing. So instead of taking one measurement for each input, we take several measurements of the state during the unitary evolution. So we can expand times V, which is the number of virtual nodes, the output layer of the preprocessing layer. So here we consider 7 virtual nodes for each input injection. And not only as we can see, the memory is enhanced. Now, with using only X measurements, we have information of the 3 directions of the input. So now, just measuring along one axis, we have all the input information. So this is reflected also in a boosting on the hybrid performance. Now, with time multiplexing, measuring along Y, we have a notorious improvement, and also with all quantum tomography, because now we have memory, and the delay distribution between the quantum and the classical part is also beneficial, at least one delay. And this is not only restricted for nonlinear tasks, also it's reflected in linear tasks, as we can see here, if we consider the state memory task, and we consider here the fidelity from the reconstructed state from the tomography that we have that we get and the actual target. And you can see here performing the infidelity. So how close it is to 1. We can see how there is also improvement in the linear tasks. So now we analyze the delay distribution to see how important are the quantum server computing and the classical part in this hybrid architecture. We don't analyze the case with no memory because obviously giving all the memory to the classical part is the best case scenario. But if our system has memory, we can differentiate 2 cases. This one that is the nonlinear task or the purity memory task, that you can see that in this case, the quantum memory is similar to the classical memory. So the best case is an even distribution that is represented by this pink line. Whereas in this linear task, we can see how representing the fidelity, we can see how the best case is setting all the memory to the classical part. And this is because the classical memory is much larger than the quantum memory. So it depends also with the size and the performance of each component of the hybrid. The similar story is told by analyzing the reservoir size of each component. So if we just focus in purity memory task and consider 3 representative cases of quantum reservoir are classical sizes, we see that with no memory, the hybrid setup is strongly constrained by the quantum reservoir memory. So even if we increase the number of echo-state neurons, the delay at tau 2 or greater fails because there is no memory with even distribution. And quantum if it has memory, we can see how time multiplexing allows the system to sustain a larger performance. Here, for instance, up to delay 4, we have a normalized mean square error of 10 to the minus 1. So both sizes of the reservoir are important, but in different ways. As you can see here, increasing the quantum part actually shifts the normalized mean square error because what we are actually doing is sending to the echo-state network a better estimation of the quantum input. Whereas if we increase the echo-state network, it's more reflected in a memory improvement in long-term memory. Okay, so far we have considered 1 qubit input, and we want to see if we increase the complexity of the quantum input, the performance of the hybrid architecture still performs faithfully. So now we consider a 2 qubit input state, that the map is the same. Now we have partial trace over qubit 1 and 2. And the pre-processing task now is the complexity is increased because it has to predict 15 values of the quantum input, which is the full tomography. And this allows to study a more important feature in quantum information. This is entanglement. And we consider the concurrence as metric, where 0 means 0 not entangled and 1 maximal entangled. To show this plot may seem crowded, but if we just focus on the classical part, which is this, where all information are injected, we can see how now, due to the higher input dimensionality, the echo-state network struggles with dealing with nonlinearity, the memory, and this dimensionality reduction, because now the echo-state network is reducing the dimensionality from 15 to 1, that is the output quantity. But as you can see, this hybrid value restricting with time multiplexing and restricting to y-axis can at least sustain this performance 1 or 2 delays. And this is because in this case, we have set all the memory to the quantum part. So when the echo-state network struggles, the quantum part can be helpful to maintain the memory. And the same for linear tasks, but in this case, since there is no dimensionality reduction and it's linear this task, now the echo-state network is able to produce high fidelity up to tau 8 more. But in general, we can see how the hybrid advantage. Here we don't see this green line because it's all up with this blue line. And the hybrid advantage is presented with partial information, even with high input dimensionality. But as you may notice in this last plot, we have a long memory in stereo construction, but a short memory in nonlinear. So why we cannot reconstruct the nonlinear feature from the state that we are reconstructing? In other words, we want to see if we compute the purity from the state that we are reconstructing, there is an improvement. So here we compare the case that the target of the hybrid setup is the purity directly, and here computing the purity by targeting the state, which is the state memory task that we mentioned before, for 1 qubit and 2 qubit. As you can see, recalling the purity at present state for the 1 qubit case is very similar. But for the 2 qubit input state, we have an improvement of 2 orders of magnitude. And as you may note, the most important thing is that we can sustain this performance for a larger memory. But it's important to recall that this brown line requires a post-processing step. So we have to compute manually the purity from the reconstructed state that we have achieved. So what we have covered in this presentation, we have achieved quantum computing with quantum inputs, thanks to an hybrid quantum classical architecture that can process nonlinear functionals of the quantum input due to the input tomography structure of the quantum reserve computing and the high memory that and a strong nonlinear processing of the Goldstein network. Also, we have seen that time multiplexing it's very important to enhance the quantum reserve computing memory. And also, we have shown an alternative approach to computing these nonlinear features that can be really difficult for quantum input, for quantum input values. As a future aspects to consider, we can explore deeper limitations, deeper analysis in memory, scalability, and nonlinear feature extraction. Also, we can consider a more realistic protocol, more focusing in the time multiplexing measurement, because it requires doing more measurements in the unitary dynamics, and this can distort the system. And we can use a more realistic protocol. And also we can investigate correlated quantum inputs or alternative reservoir models to have quantum reservoir computing with larger memory. And as a final insight, we can see if extending this favor to classical time series can also be beneficial or not, depending on the situation. So thank you so much. This is everything. Do you have any question? Pardon.
Okay, so now it's time for questions. So the committee is going to ask you some questions related to your work.
Okay.
I think that we can start with Miguel.